Hey everyone, welcome back to physics. This is going to be lecture 1 of the course, and in this section we're going to begin really our chapter 1 content, which is beginning the study of motion. And we're going to start with the simplest kind of motion, and that's going to be motion along a straight line. So let's go ahead and jump into it. We'll call this section 1.1, Displacement, Time, and Average Velocity. Okay, so we're going to begin with just a simple example, and the simple example of a car moving along a straight track. So consider a car moving along a straight track. Okay, so i.e. motion in a straight line. So it's moving down a straight track. There's no depth or width to the track. It's an idealized straight line motion. Okay, so we'll say the car moves from point 1 to point 2. Okay, so we'll just create some kind of a label here. Okay, and we can model the motion of moving from point 1 to point 2 as movement along the positive x-axis. So let's put the origin here, and let's say this is the positive x-axis. Okay, so what we're doing here is kind of a fundamental thing that you'll have to do in physics, and that is the coordinatization of the problem, right? So what we're doing is we're saying we have a car moving along a straight track. We can think of it as existing within some kind of a coordinate system, and specifically because it's motion along a straight line, we can just consider the positive x-axis. So our starting point, point 1, is somewhere on the positive x-axis, and our ending point, point 2, is also somewhere on the x-axis, right? And we can think of everything in relation to the origin. So let's say point 1 is, we can label it x1. That's the distance from the origin to our starting point. And for x2, it's going to be the distance from the origin to our ending point, way out here. Okay, so that's x2. And the first concept we really want to explore here is this notion of displacement. The displacement is, you can think of it in terms of this picture as the distance between the starting and ending point. Okay, and so we'll frequently denote it as delta x, meaning the change in x. And in this case, it's going to be equal to x2 minus x1, right? And it really is this distance, isn't it? Right, so it goes from point 1 up to point 2. That's what we mean by the displacement. The displacement of the car is delta x equals x2 minus x1. Okay, and we can again think of displacement as a vector that moves from the starting point to the ending point. So kind of as an aside to this example, let's consider an example in more elaborate space. So we've got point 1 and point 2, and let's say we take a very roundabout path between those 2 points, right? So not a straight line. The displacement is still going to be just that distance between the two. Okay, the displacement is always the distance, straight line distance, between P1 and P2, meaning your starting and ending points. Okay, so in the case of motion along a straight line, there's no need to consider this, the actual distance traveled versus the distance between the starting and ending points, but because it's all in the straight line. But in general, displacement is different than the distance traveled, because the distance traveled could be, a roundabout sort of distance like this. Okay, so again, we can think of displacement as a change in position over an interval of time. Displacement is really a change in position over some interval of time. Okay, and so we'll be thinking about position a lot. We'll talk about displacement, position, almost kind of use that terminology interchangeably. And so from the notion of position, we can develop the idea of the average velocity, right? So we can talk about the average velocity of the car over the time interval that it takes to go from P1 to P2. We can talk about the average velocity of the car over that time interval, and we can think of it as another vector quantity whose x component is the change in position divided by the time interval. So this would be the average velocity. So the average velocity, and I'm going to denote it as x, meaning that's the x component. Now, in straight line motion, really there only is an x component, but in general, there may be other components. But in the average velocity is really just going to be the change in position, so x2 minus x1, divided by the time interval, so time 2 minus time 1. So this is how far you go, and this is how long it takes you to go that distance, right? And so obviously you get a rate here, and that is the velocity. Now another way to denote it is delta x over delta t. Okay, and then keep in mind here that the x subscript, this subscript indicates that the calculated quantity is the x component. Right, so once we move into motion in 2 or 3 dimensions and higher dimensions, you'll note that velocity as a vector, it'll have x, y, and possibly z components, right? So right now we're really just dealing with the straight line notion, and so you really just have velocity as an x component. Okay, very good. So let's plug in some numbers and do some calculations here. So let's assume that P1 is 19 meters from the origin, and P2 is 277 meters from the origin, and let's let T1 equal 1 second and T2 equal 4 seconds. So given all that, the average velocity would again be x2 minus x1 over t2 minus t1. So you plug all of this in, you get 277 meters minus 19 meters. That's the displacement. And you get 4 seconds minus 1 second. And so what does this all turn out to be? Well, you got 258 meters over 3 seconds. And so you see that in this case, the average velocity would have been 86 meters per second. So the average velocity is positive in this case, right? Meaning that the car is moving to the right on the positive x-axis as we've drawn it here. Okay. So in this case, our coordinatization of using the positive x-axis makes sense, right? The car moves from left to right, so we get a positive average velocity of 86 meters per second. Now, what happens if let's plug in some different numbers just to kind of see what happens if the car is moving in the opposite direction. So let's let P1 instead equal 277 meters. So, i.e., wherever it ended in the first motion, that's our starting point for the second motion. And we'll say position 2 is then 19 meters, right? So it's going to go back to where it started. And let's say that time 1 is equal to 16 seconds and time 2 is equal to 25 seconds. So it goes out to this position of 277 meters. It kind of stops there for a while, and then it heads back the other direction. So what is our average velocity over this time interval from 16 seconds to 25 seconds? So our average velocity here, again, same formula, x2 minus x1 divided by t2 minus t1. So the starting position, or the ending position minus the starting position, ending time minus starting time. And that's going to be, in this case, it'll be, we ended at 19 meters. We began at 277 meters. And our time was 25 seconds minus 16 seconds. Okay, and so you can see this will give us negative 258 meters over 9 seconds. And so that's negative 29 meters per second. Okay. So in this case, we see that the average velocity is negative, which indicates what? It indicates that the car is moving right to left on the x-axis, or backwards. So the negative velocity indicates that the car is moving backwards, right? So backwards relative to our coordinatization. Now, it's important to note that this is all really a consequence of how we've set up the problem. We could just as easily have set it up in such a way that we could have used the negative x-axis, for example, as our coordinatization. We could have put, we could rearrange our starting and ending points so that, you know, things would come out positive. So, for example, we could have done something like this. Here's 0. We could have put P2 here and P1 here, right? So then this would be x2, and this would be our delta x equals x2 minus x1, right? And that meaning that this therefore would have been x1, right? So we could do things differently if we wanted to, right? And if we did it this way, it would flip all of our signs. Okay, so the point I'm trying to draw out with this is that it's important to know the implications of your chosen coordinate system, right? So depending on how you set up your coordinates, you could get different answers, different signs, and you have to interpret them appropriately given your coordinatization. Okay, very good. All right. So with straight line motion, we'll usually we'll usually call delta x the displacement. Right, we'll usually call delta x the displacement when we're talking about straight line motion. And we'll usually call v average, the average velocity over the x coordinate, we'll usually just call this the average velocity. Okay, now this is only with straight line motion. Right, this convention really doesn't hold any longer as soon as we move into higher dimensions. Right, so once we move into higher dimensions, this terminology or this convention of referring to delta x as the displacement will kind of break down, as you'll see. Right, in 2 dimensions, in Cartesian space, where you can move up, down, back, forth, the displacement will have a y component in general. Okay, very good. So let's take a look at a position graph. Let's take a look at a graph of position as a function of time. Okay, so let's say I have just the first coordinate here. We'll make this the time axis, and we'll make this the position axis. Okay, and let's say I've got my starting point and my ending point. Okay, so it's important to start thinking about problems in the context of position graphs and then later velocity graphs, etc. So this would be my time 1, and this would be my time 2, and this is, of course, my change in time, my delta t. Right, so that's going to be my t2 minus t1. Okay, you can kind of think of this as existing like in this triangle, and so that means this is my ending position on the position graph here, on the position axis, and this is my starting position. Right, so that means this is my delta x, my displacement. Now, it's very important to interpret this properly. This is not this is not a path of the car, right? This is just a function that tells you how far away from the origin you are. So at time 1, we were at this distance from the origin. At time 2, we are this distance from the origin, all the way from 0, 0 up to this position up here, up this spot here. All right, and so we have to start thinking about position relative to time in this sort of graphical way, because in the next lecture we'll get into instantaneous velocity, and this will be how we kind of set that up. So this is a graph of the car's position as a function of time. This is a graph of the car's position as a function of time. Okay, this is not its path. Very important. Okay, this plot shows us how far away from the origin the car is at any specific value of t. Okay? All right, very good. So that's an introduction. That's an introduction to motion along a straight line. In the next lecture, we're going to get into instantaneous velocity and kind of develop these ideas a little bit further. We'll see you then.